Hello, and welcome back. These last few months have been spent almost completely inside Manifest's physics engine, paying back most of the tech debt from the initial building process. While the engine is not fully ready, I would like to take today to talk about a specific problem that gave me some troubles, the Quickhull algorithm. The implementation is based on Dirk Gregorious' 2014 GDC talk, which is incredibly technical but very informative, and because of this, I will be leaving a link to the talk rather than reiterating most of what he says. Primarily, I would like to focus in on some of the more glossed over details that were left out of the talk for time's sake. During the process of working out this algorithm, I didn't find much in terms of implementation details aside from Dirk and his resources, so hopefully this video can serve to fill that gap a little bit. With that being said, let's jump into the overview of Quickhull. The algorithm itself is actually very simple. There are two steps for preparation. First, create a simplex from a point cloud, and then partition the remaining points outside the simplex to the face visibly furthest. Once the algorithm is prepped, the rest is handled in a simple while loop. The loop continuously checks that there is some vertex to be added, and while found, adds it onto the hull. At a high level, this is the entire algorithm. The major complexities of the algorithm I found really lie within two parts of adding the point onto the hull. The first being how to find the horizon of the conflict point, and the second is properly merging faces and handling all the pointers. Taking a look here at the original Quickhull paper, we see the process laid out in a much more detailed manner, but more or less it is the same thing as before. Specifically, looking at this line here, the boundary of V is the set of horizon edges H. This is a very critical part of the algorithm, as right after this, each edge of the horizon is then used to create new faces of the point being added. And if you watch the linked GDC talk, right around 22 minutes, the horizon and traversal methods are discussed. Ultimately, it's a depth-first search against the edges and twin faces for visibility. The next difficulty that was encountered was merging concave and coplanar faces. Dirk innocuously in the talk mentions that the majority of the complexity in the algorithm comes from not introducing dangling pointers. He does a great job of explaining the actual face merging process, but just like finding the horizon, skips over some of the more technical details for time's sake. Now, while conceptually the process of finding the horizon really isn't that hard, I found a couple of things difficult when writing the actual code. The lesser of two evils I ran into was determining if the face was visible. If we look here at the paper, which I neglected to do at first, it is very helpful and points us in the direction of testing the point against the plane to determine visibility. In case you didn't know, a normalized plane has a nice property where the dot product of it and a point in space will give you the assigned distance of the point to the plane. A positive distance puts the point above the plane and a negative distance puts it below. Also for brevity, I will quickly show how to normalize a plane. Alright, so given a plane in the form of f and d, we can find the normalized form of the plane by simply taking the n, which is the normal direction of the plane, and then d, which is the distance from the origin to the point on the plane. By taking that and simply dividing it by the magnitude of n. What that's going to result in is the normalized direction vector, and what I interpret this to be as the normalized units of distance from the origin to the plane. So for any point q on the plane where f dot q equals 0, you should get back this distance. This is, by the way, the geometric kind of interpretation that comes from Eric Lengel's Foundations series. And this would be the algebraic interpretation of it. So it's really a matrix multiplication of 4 by 1 and a 1 by 4, where the plane is a four-dimensional column vector and row vector, and the point is a four-dimensional column vector. And because we know that any point on the plane has to equal 0, we can move this value d over, and that's how we get this notion that if the point is on the plane, the distance will be negative d to the origin. So for any point not on the plane, this distance here would be some multiple of d onto the direction vector n. The second problem I ran into was finding the newly created twins. However, we can use some topology and domain knowledge to our advantage here and realize we only need to find twins for edges connected to the conflict point. The edges on the horizon remain with their twins. Alright, so looking here, this is an example from the slides where the conflict point is being added onto the hull and new faces are being created from horizon edges E0, E1, and E2. Since we're using half-edge meshes, we're essentially looking to pair the edge with one that begins in the opposite direction, starting from the edge's next pointer's tail, which essentially looks like this. Because the faces are built in an oriented manner, we can use the conflict point as a sort of anchor and determine if we're checking for an incoming or an outgoing edge relative to it. So in the code, first a check is done to see if the current edge starts at the conflict point. If so, a twin is detected if the potential edge essentially begins where the current edge ends. If the edge does not begin at the vertex, the potential twin is checked to see if it does, as well as checking its next pointer's tail to see if it begins where the current edge does. If no twins are found, null pointers return, and later when the twin is built, both the twin pointers will be set. And that should just about cover everything with the horizon. I will also be leaving a link to the Quickhull code below in case you want to see the full implementation and the DFS search. Next, we're going to take a look at the face merging process. For each edge of each newly created face, perform the convexity check described in the talk by checking the centroid of each plane is below the surface plane of its twin and vice versa. If either face is detected as being non-convex, merge the twin face into the current face. Once you perform the initial merge, some topological violations may be introduced into the current hull. To check for these, determine if any two edges of the face now point to the same neighbor face. If this condition is detected, then the polygon is checked to determine which topological correction we're going to perform. Triangular faces will perform another merge, again the twin into the current face, whereas polygonal faces retain their face, however merge the incoming and outgoing edges together. Like the horizon, conceptually it's not the worst to understand, but handling the edges to avoid dangling pointers creates some problems. So the initial merge process I'm not going to go over as the slides for the talk actually have the pointer assignments you need, but I will be leaving a link for the slides as well as the talk. However, the topological violations are not so clear. So here, this is the triangular case, and we get something like this where we want to preserve the external edge of the twin face. So to handle this, we first update the face to remove a potentially dangling pointer. If the current face points to an edge we're going to remove, we know that the previous will remain, so we just make it that. Then we find the external edge of the triangle by simply looping until we don't have either the incoming or the outgoing edge's twin. Then once we find the non-shared edge, we can merge it into the current face by making the incoming edge's previous next pointer and the outgoing edge's next previous pointer the non-shared edge, and then we can update the non-shared edge respectively. And for the polygonal case, we're essentially just going to be stretching the incoming over the outgoing and extending it to where the outgoing ends, making these two twins of one another. So for the pointer assignments, the same logic applies for the face. However, we also need to update the twin's face edge pointer as well, since it may also be removed. Then for the edges, The outgoing edge as well as the incoming edges are going to be the two edges we're removing from the polygon, or from the two polygons. So the pointer assignments are fairly straightforward. The incoming goes to the outgoings next. The previous pointer for the outgoing next is set to the incoming. And then the outgoing twins next pointer is set to the incoming twins next. And then finishing with moving the incoming twins next pointer to point to the outgoing twin. As Dirk said in the talk, the major complexity of this algorithm comes from not introducing dangling pointers. So that should just about cover everything I wanted to mention for Quickhull. As I said, the talk does a really great job, but there's just a lack of readily available resources to iron out those last few technical details. There is probably going to be another gap between this upload and what comes next, which I'm planning on being the redesign of the physics engine's contact detection scheme. After that, I am hoping to finally have the foundation set to move into some actual game-related development, but that will be pending the contact resolver. However, I don't want to get too deep into that now. Nonetheless, thank you all very much for your time, and I will see you in the next one.